Before we dive into section 6.4, remember on Monday I talked about I had the grade book screwed up and I fixed it over the weekend or that morning or whatever. Well, I didn't for this class. I done it for one class and I screwed it. I apparently didn't do it for any of the other ones. So I ended up figuring that out on yesterday. So I fixed everything, and now if you saw a grade change, that's what the grade change was fixing that. My apologies again. It was not my intention to mislead anybody or have the wrong stuff posted. It's accurate now, and it'll be throughout. I'll find a little opportunity to have some take-home test points we'll give you guys here in the coming week or two to help that test category out a little bit. Get you some, something where it's you have some time, you look stuff up, and go slow and get some good tests, so we get some more test points in that category and help even things out. In addition, test 6 will be probably do that take-home thing next week. It's just like a homework assignment or whatever. And then we'll be looking at the chapter 6 test probably beginning of the week after. And then this thing that'll be coming in. So there's a whole flood of more test points coming in. So if you're not happy with kind of where your grade is at, there's 3 opportunities there in the next 2 weeks to affect that space if you're not happy. Okay. Again, my deepest apologies for telling you that I fixed it, not really fixing it, and then having it hit later. Again, that's not my intention. Obviously we'd like to believe we do it right the first time. Today, we're going to cover the last topic for test 6. So this is like a physics section. How many of us are currently in or have ever been in physics before? Nice. Okay, so I'm going to ask you guys a bunch of physics questions during this, and I'm going to hopefully get some good answers from you guys. Don't look so nervous, it's fine. So, in this section, mostly what we're talking about is calculating work. In physics, how do we calculate work? Force times distance, right? It's how far you have to move something and how hard it is to move it. That's work. So in most of your physics class, force is constant. What if it's not? How are we going to calculate the work done over some distance if the force is not constant across that distance? Well, we're going to take little chunks of that distance and find out how much work was done over that little tiny chunk of distance, and then add up all those slices. What does it sound like we're doing here? A Riemann sum, and if we take those slices infinitely thin, then we're talking about an integral. So basically, we're just integrating force over the distance. Is everybody okay with that idea? So, let's start looking at some examples, right? Standard non-calculus-based physics question. How much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that's 0.7 meter high? Use the fact that acceleration due to gravity is 9.8 meters per second squared. So we know force is mass times acceleration. So in our case, that would be our force, right? Gravity is constant, or we'll assume it is anyway. Elevation matters a little bit. Everybody's okay? So the work then would be force times distance. whatever that number is. And our unit for work is joules, is our metric unit. Everybody okay with that? That's the same thing as newtons times meters. And newtons is our force unit. I know this is a lot of physics for those of you that are not physicsing. Part B, how much work is done in lifting a 20-pound weight 6 feet off the ground? It's a little bit of a different question. Physics students, what's the difference between mass and weight?
Weight is like gravity.
Weight is a force. Mass is just a quantity, right? Like weight is a vector. Mass is a scalar. Everybody's okay? So here, 20-pound weight is given to me as a force. 20 pounds is a force. So my answer would just be 20, the force, times 6, the distance. So I'd have 120 foot-pounds. That's our English unit work unit. Equivalent to it. I mean, it's not the same as a joule, but it's like it's also a unit of work. Just in English units rather than metrics. Everybody okay here? Now, what if it's not force isn't constant? Well, then we can just take the integral of that force function times the distance. The distance is dx. That's like our little tiny slice of distance over the change in distance from the starting distance to the ending distance. So that's like our upper and lower bound here. Is everybody okay? So if we look at example 2, it says when a particle is located a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done moving it from x equals 1 to x equals 3? So my work function is force times distance. Whatever that comes out to be, I'm going to skip that because this is an integral we should be able to handle pretty comfortably on our own, right? And my unit here again, because we're in feet and pounds, my answer would be a foot-pound, or be in foot-pounds. Does that feel okay to everybody? Again, we're just integrating force times distance, where the distance is that dx slice, right? Is okay? Physics students, have you talked about springs with forces? So the property that governs how springs behave is called Hooke's law. And it states the force required to maintain a spring stretched x units beyond its natural length is proportional to x, i.e. the force is a function of x, which is equal to k times x. Are you okay with that notion? We call k the spring constant. So it's basically describing like how stiff that spring is, right? The stiffer the spring is, the harder it is to stretch it out and keep it held stretched. The looser that spring is, the easier it is to stretch it out, right? Is everybody okay there? All right, so let's notice here that this is a function in terms of x, right? The force to hold a spring is not constant. It's dependent on the distance pulled past its natural length. So if I look at example 3, it says a force of 40 newtons. So that's a force unit, for those of you that are not familiar with physics. So this is a force, tells us that in a problem. is required to hold a spring that has been stretched its natural length of 10 centimeters to a length of 15 centimeters. This first sentence is just giving me a way to solve for the spring constant. So 40 is equal to k times x. What will x be in this case? Right, the displacement. So I should write it as what?
Dude, ready. Oh, sorry.
Not 5. Units matter, right?
Centimeters.
It's the unit is in centimeters. What unit is newtons in? A newton is like a kilogram meter per second squared. So I need this to be in, the distance needs to be in meters. How do I convert 5 centimeters to 5, or to meters? Divide by 100, right? So K is 800. Okay? 1 or 0.05 is 1/20th. So that's by 20. Now it asks how much work is done stretching the spring from 15 to 18 centimeters. So it's just the integral of force times distance. Again, my force is the 800x, my distance is the dx. And because we're going, our unit needs to be in meters for distance, I convert the 15 and 18 centimeters respectively into meters. Everybody's okay? All right. Example 4. This is a bit more complicated. A 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? Important observation. I pull 1 foot up of cable. How much cable is left? 99. How much does that remaining cable weigh? Less than 200 pounds, because a foot of the cable is now sitting on the ground next to me, right? The remaining cable that's dangling is 198 pounds. Dangling, right? Does everybody understand? Like if you're trying to help a friend who's hanging over the cliff, if they get a hand on top of the cliff and they can take some of the weight off of it, there's less weight dangling, right? If they get a hand and a foot up there, it's even easier to pull them back up, right? Do you guys, does that make sense intuitively if we think about it? Okay. So, if so we know that, what do I want to say this? Force equals, we want to say f of x is equal to like k times x here, right? And we know that like 200 is equal to k times 100. So 2 is k, right? So that's the weight, right? Everybody okay there? So our work should be then just the integral from 0 to 100 of 2x dx. So when we move it 100 feet, I have to move 200 pounds, right? When I'm moving it 0 feet, I'm moving 0 pounds. If I move it 50 feet, I'm only moving 100 pounds of cable. Does that make sense? So that should be it. And again, what unit should we be in here at the end? Feet and pounds, so there should be in foot pounds. Am I out of time here? We'll finish this next time then.